Okay, so where energy comes from is such a silly explanation. No one even wants to believe it. But what energy actually does is it keeps track of everything that's changing in the system independent of time. And so that was the goal for a while. They derived this long, long ago. Let's see, if you want the really long explanation, that's chapter 7 in the book. I'm trying to learn to write neatly. But we already, so they wanted to keep track of time, but especially with crude clocks, time is difficult to keep track of. So they thought it would be even better to figure out what's changing and what's happening in a system without having to keep track of that. Can we find things that are constant over time, or conserved is the word? Well, we already have an equation that keeps track of everything, or at least particle by particle, without time, and it's number 3. Very good. If we're in the x-axis, it's 2a delta x. But now we know, what produces acceleration? I have to have a net force, or this is AP physics, so I'm going to subject you to sigma. The sum of the vector forces divided by the mass, that's what causes your vector acceleration. Okay? So how about we put the mass back in there? Right? I'd rather measure force or maybe mass and not just acceleration, right? Because acceleration is change in velocity over change in time. I'm trying to get away from measuring time. Okay, that's really difficult. We've got some laser systems in there and stuff. So let's multiply everything by m. So I've got mv squared. We'll take one mass, one object at a time. We can always take it out of the experiment. Times 2 times the net force times the displacement. And I'm actually going to start writing displacement, this as a dot. We'll explain that later. There are different ways to multiply vectors, and they're signified with a dot and the x. They didn't teach you in 5th grade or whatever. There's the x, and they taught you the x and the dot both mean multiply. They actually mean different ways to multiply. But, like what? There's different ways to multiply. With normal numbers, there's not, which is why that didn't matter in 5th grade. But when you have vectors, it is. Well, wait a minute. It's easy to measure force and displacement. I'd rather not have to double that all the time. Let's make this other thing carry all the extra terms. So let's divide everything by 2. And instead, I'm going to write 1/2 mv squared minus 1/2 mv0 squared equals the net force times the displacement. If I can write an x. Oh man. And we're going to make up fancy names for this. Whoops. Everything shrinks. We're going to call this force times displacement the work done. And 1/2 mv squared is just a mouthful and too much to say. So we're going to call this, and it's got a minus sign, and it's final minus initial, which is the change. So we're going to just call this one the change in energy. It's literally like the French word énergie, movement, energeticness, whatever, energy. We're just going to call that energy. Stuff is moving, it has mass. We throw in a 1/2 because it comes out of the equation. Okay, it's because it's actually the average. I remember that came 1/2 at squared. That's that because you have the average velocity, average acceleration. Okay, so there it is. Force times displacement, net force times the displacement that actually happens is the work done. Okay, and then you do 1/2 mv squared, subtract final minus initial, and that's your change in energy. This is called the Work-Energy Theorem. because the French scientist that made it up. College Board expects you to know that that's Work-Energy Theorem. It's not as common as Newton's second law on free response equations, but sometimes they'll say, using Work-Energy Theorem, derive this. Well, they just want you to know, change in kinetic energy, we would say delta KE. Oh, these have silly new names. That'll be the next slide. Okay, equals the work done. Okay. Well, old Isaac Newton came along and said, that's silly. You can't always multiply those things. And what if your net force isn't constant? What if your displacement is something weird? If your force, like in a spring, is a function of x, then you actually have to do the antiderivative of force with respect to x itself. And that counts as your displacement. Okay. The first problems I have for you to do are just one dimension usually, or or a simple combination of the two. So don't worry too much about it. It kind of comes out naturally. Any questions so far? All right. Work-Energy Theorem, and we got our integral. And that took 6.5 minutes. Okay, does anybody still need that slide? Okay. Real physicists hate this F sub t and F sub f and stuff. In fact, so College Board is working with us, and they no longer use KE, right? That was notation in your first year. I probably said KE for kinetic energy to help you remember what that was. We just say K. And we could say K0 for kinetic energy. Or on our Work-Energy theorem, we just say delta capital K for kinetic energy. Pretty easy. For potential energy, in AP Physics, we typically don't have the nice MGH. Sometimes we do, or the spring that was 1/2 kx squared. Sometimes we do. Those are still fun examples. But in theoretical physics, we need a potential energy function of x. And since F was taken and K was taken, they called it U. Potential energy is now capital U, and it's actually usually a function of R. Oh yeah. No, let's leave it x for now. This line, okay. It's still the force, which is probably also a function of x, dotted with dx. Okay, and College Board writes it U of R F dot dr. Okay. Yes, that looks terrible, except that R is just x, y, and z. Oops, I don't need the arrows if I drew the brackets. Ah. That's what they mean by R, but actually it's usually going to be a function of just one of those. Just x, just y. Most systems reduce to x, y, or z. We can handle it in one direction, or we can make it r and do the radial direction. With gravity, a lot of times we're going to need radially inward, radially outward. Okay, so we reduce it to one dimension whenever we can. Okay. But this actually means, if you have, by the fact that these are vectors, and this is what F dot dr means. It means the force in the x direction, dx, plus the force in the y direction, dy. Everything is separated by components. That's what the dot means. And so the other one is cross. Okay, when you do a cross product, the directions literally cross. And when you do a dot product, everything is separated into its own dimension. So this is the easy one, only one we're going to do at first. Okay, we don't need crosses till later. But it just means put every dimension in its own compartment, and you do them all. And so if I integrate them all, I just integrate one by one. And usually, like, x and z will be 0 if we're doing a vertical problem. Like if there's only the force of gravity, the net force, then then we only have y. Or if there's only some horizontal force, then we only have x. And the other ones are usually 0. So don't panic. Let's see. I think I wanted to do an example with the inclined plane. And then we'll be done. But I better break my video or it's going to go over 15 minutes. Any questions so far? Here, I'll freeze that, stop the video.